Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, Ricardo Lopes, and today I'm joined by Dr. Craig Callender. He is Tata's Chancellor's Professor of Philosophy and founding faculty and co-director of the Institute for Practical Ethics at the University of California, San Diego. And today we're talking about the philosophy of physics with a focus on time and also how it compares to our intuitive model of time. So, Dr. Callender, welcome to the show. It's a pleasure to have you.
Hi, thank you very much, Ricardo. It's a pleasure.
So, before we get into the physics itself, just to talk a little bit about how we as humans intuit time. So, we have this, or we tend to have this model of time where we think about it as a flowing present that divides a fixed past from an open future. I mean, comparing it to physics or how we think about time in physics, I mean, how close is it?
Yeah, I think I think at the kind of fundamental level, it's basically wrong.
Okay.
Yeah, so in my book, I call this model manifest time.
Mhm.
And I don't mean it necessarily as like manifest in the sense of the time you observe, but sort of like this sort of more common sense model of
Yeah.
time. And so, yeah, you think that this moment we're talking right now is, distinguished in the world. It's the only thing that's happening, and that it divides the world into two. And it's the present but it divides, the past from the future,
Mhm.
and the past and the future we tend to think of very different from one another.
Yeah.
So the past is fixed, the future open. And then we think this whole structure just kind of updates itself and moves. Yeah, and then I think, well, that actually, from the point of view of physics, I think is at well, it's wrong.
Okay, so then what is the correct view of time? How does time actually work in physics?
Yeah, so if we can look at different physical theories, but if we
Mhm.
think of relativity as sort of the theory that explicitly tackles time, then on the in a relativistic universe, what you have instead is a bunch of all of the events of the universe all sort of laid out in this kind of four-dimensional manifold, and you don't really think of um, time as a fundamental aspect of this.
Yeah.
Famously, Minkowski said, with space, that space and time were doomed to fade away into mere shadows. And so in a relativistic universe, you don't need this kind of, you don't have a distinguished moment of simultaneity, but really the common sense picture is more than about simultaneity. It's about, a kind of distinguished now, which is like an indexical, so now is now, but now is now. And so the physics, even before relativity, didn't make use of distinguished now, even when you had simultaneity, like in classical physics. So I think even classical physics shows that our common sense conception of time is not right, or at least it's not, it doesn't vindicate it, maybe I should say. Um, and Yeah, so in physics but then relativity is sort of makes it even worse for common sense time. It's not only it makes it harder to, if you think of like common sense time as a kind of model and you try to like graft it onto the
Mhm.
relativistic universe, it's very hard to do that in a non-arbitrary way.
But I mean, compared to the way we commonly think about time, I mean, our sort of folk physics, let's say, does time actually have a direction or even or a fixed direction or not?
I think according to the kind of folk model, it definitely does.
Hmm.
So I think of So I'm thinking of the folk model. I'm thinking of, past, present, future, and then that distinguishes the future from the past in a kind of intrinsic way.
But then, I mean, what about the model that we have in physics? Does it have any direction or not?
Well, it yes and no. So
Yeah.
I think that there are. So when we think about that in physics, we ask, are the laws what are called time reversal invariant? And so if viewers want to think of it intuitively, just think of like a kind of film. You have a film of the universe, and then you run it backwards.
Yeah.
Is what you saw backwards also a solution to the laws of physics? And if not, then it seems like the laws care about the direction of time. And so when it comes to some of the big famous equations, fundamental equations of physics, it seems like they are time reversal invariant, that if I ran everything backward, it would be possible.
Yeah.
That's certainly the case of classical mechanics. But there are these, phenomena in quantum field theory that do seem to be not time reversal invariant. And then there's this other symmetry people talk about called CPT, which is the combined operations of flipping charges, flipping spatial handedness, and then flipping the direction of time. And then physics is invariant under that. And so if that is sort of like the modern version of thinking of time reversal invariant, then then physics is invariant under that. That is, if I gave you a movie of the universe, and then I switched all the charges, positive to negative, switched all the hands from right-handed to left-handed, and then switched the direction of time, then you couldn't tell the difference between the two. And so, well, anyway, yeah, so that might clash with our ordinary conception of time, that firmly has a direction in it.
And where does time come from exactly? I mean, how does time arise?
Yeah, I guess I think there's no real answer to that question. So if I think of time as just a kind of non-fundamental aspect of space-time, and then if I translate the question to where does space-time come from? And I think, well, space-time just is. And so it's a bit like, why? Then the question becomes more like, why is there something rather than nothing? Or why is there being rather than non-being? And then I just think there's not really an answer to that question. We've reached a limit at that point.
Yeah, but when it comes to the space-time continuum, I mean, I'm not sure if this question even makes sense, or at least the way I'm going to put it, but how does time relate to space exactly?
Yeah, so it's if you how does time relate to space? Yeah, so they're two different dimensions of the space-time continuum, and so they're but there's not but in relativity it's not like you just sort of in classical physics you could sort of think of like the universe as like a big I don't know, a big ham or a salami, and I put it into the slicer, and I slice.
Yeah.
And each slice is entirely spatial, and there's one way to do the slicing. In relativity, you could do that kind of slicing, but it's not unique. And so there's all these other ways you could have sliced the ham or the space-time manifold. And the time is the direction in which, that's sort of orthogonal to all those possible slicings. So there's all these different ways you could do the slicing, and time is the sort of direction. So really, should speak about the time-like directions in relativity. So what directions are the time-like ones? And those are the ones that will allow this kind of slicing to happen. And so it relates to space as just, it's another, well, it's another direction on the manifold.
But I mean, what are maybe the distinctions between the space-like and the time-like directions in physics?
Yeah, so that's really a huge issue and really very important because once people think about, and people tend to go to relativity and they start thinking about it, then they think, well, yeah, time's just another dimension of the of a four-dimensional kind of block.
Yeah.
And then they think it's then, you know, like space, but it's not like space. It's got, you know, the fundamental feature of relativity is the metric, which gives the distances between events. And the distances between events in the time-like direction are of one sign, either positive or negative. And the distance between the space-like ones are the other sign. And that little sign difference, so sometimes people just talk about like there's just a minus in front of the time-like directions. That little minus sign, it seems like it's not that important, but that little minus sign is massively important. And so it ends up making all the difference, excuse me, all the difference between the space-like and the time-like directions. And so you can have, you know, there's, and what behavior, and how that minus sign then hooks into the rest of physics, like about with its relationship to mass, its relationship to the dynamics of what happens, all is very, very different. And so to me, when I see that little minus sign, I think, you know, I don't try to obscure it. I don't pretend it's only a little minus sign. I see it as really like the core difference between the space-like and the time-like. And, you know, super important, which leads to basically all the important physical, at a gross scale, all the important physical features of the physical world.
But then just to clarify one point that you made there, when people say, which is something that we commonly hear, that physics spatializes time, that is incorrect, right?
That's right. I think that's incorrect, and that saying that has led to, you know, a really a misunderstanding of relativity, and led to, you know, I think some of the less productive directions in philosophy of time. Yeah, so people have said this many times, you know, where they say, you know, so Bergson famously said that, you know, physics spatialized time. And I think, you know, there's a certain way of seeing it where maybe, you know, well, I don't think it does at all, but I think what's going on is this, you know, so when we think of the spatial, we don't think of the, we might call the kind of the spatial, the indexical terms as objective. So I say, I'm here, and here means San Diego, you're there, and you're there in Portugal. And then I might move, I might fly to Portugal, and then my here is Portugal. And no one thinks that the spatial here is important in any way, you know, objective, sorry. And so then when you get to relativity or physics, it doesn't require the indexical time counterparts of those spatial indexicals. So it doesn't require a now and a past or a future. You can just have all the earlier than and later than relations. Just like in space, you can have all the, you know, just to the right of or to the left of or something. We don't think of those as, you know, that you don't think that there's like a right side to the universe. And so when we say that physics spatialize time, well, maybe if we just meant, well, we don't objectify the temporal indexicals, well, then that might be right. But then classical physics didn't do that either. And so it's not really, so that doesn't mean that for the non-indexical stuff that space and time are treated the same way. They're clearly not, even in classical physics. So I think that we've never spatialized time in one sense, or we've always spatialized time in this weaker sense. But the important thing is that in the terms of the non-indexical stuff, we've never spatialized time, and relativity certainly doesn't do it either.
Yeah, I guess that also, I mean, many things in science are extremely counterintuitive, but probably things coming from physics are some of the most counterintuitive out there, and particularly when it comes to time and the space-time continuum. I mean, it's very easy for us to imagine a three-dimensional space because that's actually what we see. But when it comes to trying to understand this fourth dimension of time, it clashes against our common understanding of time a lot, and so it's very hard for us to wrap our minds around it, right?
Yeah, definitely.
So, I mean, what is the tense theory of time? I mean, what are tenses in the context of physics?
Yeah, so tenses are, so if we think of these temporal indexicals, like now and past and future,
Yeah.
those are called tenses.
Mhm.
And notice that they're always relative. What the crucial thing is really this idea that there's a distinguished now or present. All of the other temporal properties are all ultimately connected to this idea that there's a kind of privileged now. And so McTaggart famously in 1908 had this paper in which he talks about these tensed properties, and he calls it the A series. And notice you could look at you could organize all events of the universe and just say which ones are now, which ones are past, which ones are future. We could also do what's been called the B series, the tenseless series, where I organize all the events in terms of the earlier than or later than relations.
Mm-hmm.
So Socrates dying, that was earlier than our discussion. It was in the past. So in the first one, I'm using tenseless language. It's always true that Socrates' death was earlier than our discussion, but it wasn't always past. At one point for Socrates, it was present. At one point for Socrates, it was in the future. And both our discussion and Socrates' death were in the future. So what's one feature of this, the tense properties are that they have this kind of changing truth values with respect to what time you use them.
Mm-hmm.
And McTaggart was really ahead of his time because identifying this then became a feature in cognitive linguistics where people do look at this kind of language we use. So it's definitely a real thing, that as we use language,
Mm-hmm.
and I think and I'm not a linguist, so maybe I'm wrong, but I think it's not every language has tenses exactly, but every language has a way of encoding them in some way, as far as I understand. And so it seems to be a pretty universal feature of human language that we speak in this kind of tensed way. And you can see why, it's a good shortcut, given the way the physics of the world works and everything. If we were in the same room and I just point to some object and say it's, like blue, then I don't need to, I could say it's blue now. I don't need to say, give a whole elaborate thing about the earlier than, later than relations. And so it's pretty interesting actually, because there you can see a big difference between space and time and the way we act and think and talk. Because if I was, suppose Ricardo, we were having a dinner and you were at the opposite side of the table, and I said, please pass the salt. And you look around and you're wondering where it is, and I say, it's on your right. So there I'd be indicating that the spatial indexical is relative to, I'm understanding that it's relative to you. It'll be on my left, but it'll be on your right. But notice we never do that with time. I don't say, oh, it's in your future, not mine, or your past, not mine. And so we do use this model, and then you can then see why. So then the tense theory of time is so there's, let me back up a second. So in terms of language, there's no question we use tenses, and we speak particular ways, and we distinguish between what we might call the spatial tenses and the temporal tenses in interesting ways. Now, what does that mean? Now, sometimes what's called the tense theory of time is now supposed to then be a theory in metaphysics, which then takes those tenses and thinks of them as latching onto reality in some way. So whereas relativity doesn't have a kind of privileged now, a tensed model of time understood in a metaphysical way, it will have a special now in some way, typically. And then they come in all these different varieties of metaphysical models. So some say there's just this present and it changes in some way. Some say there's the present, and then there's a real past, but not a real future. That's called a becoming model. And then there's all sorts of other models. There's probably like a couple hundred of them, really. So that's supposed to then, these models are posited to vindicate that way of speaking that I mentioned.
But even if our intuitive model of time is incorrect, do we have a good understanding of how it develops cognitively?
Yeah, so that's what I try to do in my book. What makes time special is the whole idea. About half of the book is to basically try to come up with an explanation for why it is, even if it's fundamentally wrong, why it nonetheless makes sense for creatures like us to have come up with this model and to treat the spatial sort of tenses differently than the temporal ones, or the spatial indexicals differently than the temporal indexicals. And so for me, excuse me, for me, I think, it might be wrong, but given our environment, given our cognitive and perceptual and anatomical situation, the kinds of problems we have to solve to get around in the world, given the physics where the temporal direction is different than the spatial direction, and a whole host of other things, I try to then show why it makes sense for us to develop this kind of tensed model. And so I try to vindicate the tensed model as even, not fundamentally right, but a really good thing for us, because it helps us get around. So I, given the physics and given a bunch of other things, I just can't move on the space-time manifold in ways, or have access to information on the space-time manifold in particular ways that would. And so given these constraints, it makes sense for me to come up with this. It makes sense for human beings, but also I think animals, probably most animals, have some kind of tensed conception of time. Maybe they don't think about time, of course, but they don't do philosophy as far as I know, or physics, but they still, seem to, there's some evidence that they employ a kind of tense theory of time as well.
Yeah.
And so I think it's organisms are reacting to a very low level basic feature of the universe. And that is then, creating in them a reason to think that there is this like preferred now. It's a good organization tool for us. And for most of the sort of things as you're sort of navigating around locally, the signal speeds are very fast, and we've become attuned to our brains, and our perceptual systems are sort of adapted to try to figure out when the signals that are reaching us are coming from the same thing or not. So when somebody is like in front of you and they say hi, you'll see their lips move. So then you'll have the light bouncing off their lips going into your eye. So it's going very fast, the light, the speed of light. Then you'll hear hi. And so then there'll be sound coming from their mouth. That's then coming in very, very slowly. But your eye works very slowly versus your ear. So your ear is kind of mechanical, very fast. Your eye is photochemical, a bit slower. So that's decreasing so if the sound and the light both came from the same source, now you've already decreased the gap between the arrival of the light and the sound to some extent. Then your brain is doing all this other stuff too. And so there will actually be, some people will then bind those two and think that those two signals came together if the light comes first or if the sound comes first. And so there are light firsters and sound firsters. But basically, if it comes within a certain window, if these two signals come within a certain window, you'll tend to think that they came from the same source. You then don't need to know then, which one is earlier than or which one is later than. You can just say, oh, that person said hi now, and I don't need to relate it to some other event. If you compare that to like receiving something in the mail, if you were getting your bank statements in the mail, and the bank statements didn't say what time the bank statement was for, then the information would be pretty useless, because maybe the mailman or mailwoman put it in the box the wrong order or something like that. And so if the signal takes a long time and has all these transmission errors, then you really needed those letters, the information, dated. For hi, it said to you in the room, you don't need to say, okay, Ricardo, let's synchronize watches, ready? And then hi. You don't need to do that. You can just say hi, and it's understood that it's now. And so I look to see why it then makes sense to come, so all these sorts of considerations, I like to then see why it would make sense to come up with this kind of tense model of time and treat it differently than the corresponding model of space.
I guess that also from a biological / evolutionary perspective, we have to keep in mind that what really matters here for organisms like humans and other kinds of organisms is for them to have a useful construct of the world in ways that increases their fitness, right? I mean, of course, we don't need to have at all any direct access to objective reality. And I guess that in terms of other things that we perceive, like, for example, color, of course, a physicist would say that a color is not an intrinsic property of objects. It's not really there, but it's useful for organisms to perceive it, to move in the world, and to perhaps eat the correct things and some other aspects of their life where color plays a role. I mean, it's much more about usefulness than necessarily about a truth, or at least truth index to objective reality, right?
Yeah, exactly. That's exactly the way I'm thinking of it. In fact, very much like color. I think of
Mhm.
it as a very low level sort of thing. So that's why I think animals and that also have with color. Yeah. So I think of it very much like color. Yeah, and so I think of it as all the different animals. We're all trying to solve this an evolution. So we're trying to solve this kind of problem with we're bombarded with all these signals, and the signals don't tell us the time like a letter does, and so we have to figure it out. But if we don't figure it out, we'll die.
Yeah.
So you need to, if you if a tiger comes up and roars at you, and you're still uh, and you're not syncing the visual with the auditory, you probably die. And it'll also be very hard to catch things. And so, but probably all the different animals do this differently, and so they probably have different simultaneity windows.
Mhm.
So in the book I talk about probably the giraffe has not just a long neck but a long now, because if you just think of how long the nerves from the feet to the brain and back on the giraffe, and
Mhm.
that it doesn't go that fast, the signal speeds in the nerves. And so when you think of it like adjusting its foot uh, for where, on the ground, for bumps on the ground and stuff, and it's, that signal is like going like 18 feet or something. And so there's going to be this kind of lag. Um, and so we have the same kinds of things too. Um, but, the giraffe would be maybe more uh, exaggerated. Or seal would be interesting because the speed of sound in water is
Yeah.
very different than in air. And so all of these things should shape their maybe not whatever, they don't have a conception of time, but maybe the model of time is very similar to ours, but like the lengths of the simultaneity windows and things like that might be very different.
Mhm. And getting into a question directly related to metaphysics, how do you look at the relationship between philosophy of science and, in this case, more specifically, philosophy of physics and metaphysics?
Um, yeah, so I think of, well, that's a big question. So yeah, I think of all of physics as implicitly making very many metaphysical assumptions.
Mhm.
And so I have a bunch of things where I'm criticizing metaphysics, but it's not that I'm anti-metaphysics, because I do think that, when we look at physics, we can and pry into it, we can then see that there are all these different metaphysical assumptions within it. And so that's what I'm trying to do, is sort of unearth these metaphysical assumptions,
Mhm.
and try to see physics what physics is telling us about the universe. Um, but there are bits of philosophy, some types of philosophy of time that I think are misguided the way they go. So historically, philosophy of time, I think, has always been one of the methodologically most, I don't know if I should say this on a public thing, but yeah, like the most backward of areas.
Yeah.
So for so long, it was just doing, this kind of analytic philosophy, this kind of ordinary language philosophy, where the way the game worked was you would find out what the nature of time was, and here's how it would go. You would take a sentence, in English or in Portuguese with tenses in it, and then see if you could translate it into a sentence without tenses. And then if you couldn't, then it proved that the tense theory of time was true and that relativity was wrong or not fundamentally right. This is terrible. Why? So we know that you can't, because of the essential indexical, we know that you can't translate statements with indexicals to, you can't translate statements that are with indexicals into non-indexicals and retain the same meaning. And that argument was always bad anyway, even because it would do that. It would prove too much because you could do it with other indexicals like spatial ones and personal pronouns and things like that. And so it ended up proving too much. And so anyway, so it was like a mugs game, if you got into it, because if you wanted to defend anything but the tense theory of time, and you started to play this game, you were destined to lose. But the game was rigged because you could never do this. So then they changed the rules of the game, and maybe started to change it, and maybe, I don't know, the 80s and 90s. Then people would say, well, no, now we're interested just in the truth makers for these claims, not translating without loss of meaning. But still, it came down to some fairly similar sort of game still. And then, to me, the big thing has always been that you could posit as many models as you like, all these really elaborate metaphysical models. But what is the evidence for those models? What do they explain? And I've always thought that they were lacking explanatorily. So the core thing really is that they're all positing some kind of now or present. And the only difference between the events that are now and the events that are not now, they say usually, is that the events that are now exist and the events that are not now don't exist. But of course, existence is what kind of property is existence? Well, on the standard way of thinking, it's not a property at all. But even if you took a view where it's a property, it's a property that has no character, no essence to it whatsoever. And so but then how can that feature into the causal network of the world in any way? And so it's never going to be, most explanations are causal explanations. And so you're not going to end up being able to say that there's any kind of causal explanation for why you have the phenomena we have or the data we have. And so at best, it's going to vindicate some linguistic intuitions. Mm-hmm. But I think it's better to do what I try to do, which is try to show how this model arises in order to try to vindicate those intuitions.
So do you think that when it comes to metaphysics, we should derive metaphysics from physics? I mean, in this case, the philosophy from the science, or not necessarily?
Yeah, I don't want to make it too deferential to physics that we just look at the physics and then, derive it from there, because I think mm-hmm. sometimes the physics it's a two-way street, and sometimes the physics can be wrong, I think, mm-hmm. or not properly interpreted. So I think it's a two-way street, and of course there's more the world of science than physics too. There's biology and everything else. Mm-hmm. But I do think there has been this kind of trend in analytic philosophy where it wants to vindicate the linguistic intuitions too much, doesn't really care about how much it's going to explain. Now, people who disagree with me they'll say, "Oh, but we are explaining, just like in science, and science uses all these kind of theoretical virtues like simplicity and that too." And so they'll say, "Oh, we're all just using inference to the best explanation." But I think that that's really, maybe okay at one level that's true, but if we dive in and actually compare the kind of just absolutely brutal critical process that happens in science and just how high the standards are for scientific theory to actually explain, be taken to explain something, and then the very modest things that these metaphysical models end up explaining, then I think it's really more like night and day difference than uh, doing the same thing.
Mhm. So let me then just ask you one last question. We've been focusing our conversation a lot on time, but looking at physics more generally and as a philosopher of physics, what would you say are perhaps some of the biggest, or at least what you consider to be the most interesting unanswered questions in physics?
Oh, hmm. Well, yeah, I'd have to start with all the puzzles, that quantum mechanics provides.
Mhm.
So we have massive debates and disagreements over what to make of, quantum non-locality and, just the measurement problem. And so I think that resolving those are key to, many other things, so that what's happened is the kind of foundational philosophical questions have been sort of shunted aside for a long time. And, so you've had the Copenhagen kind of an understanding of quantum mechanics, making it so that you're not able to ask, you're not supposed to ask a lot of questions about the awkward questions about what's going on.
Mhm.
But then when you look at, you're trying to develop quantum gravity, trying to come up with a theory that will unify, or make consistent gravity with quantum mechanics. It seems crazy to me to think that what theory of quantum mechanics is actually right won't matter to that question. And so you're sort of trying to, produce this consistent or unified new theory, but you've got your hands tied behind your back because you're not allowed to speak about what one half of that equation, what that world is really like.
Yeah.
And so I think understanding better quantum non-locality is really one of the because quantum non-locality comes up in a lot of that, but the correct interpretation of quantum mechanics is really one of the core things. Um, but yeah, there's so many other questions too, but that's just one.
Yeah, but that okay. So let me just ask you a more specific thing then. Do you think that at this point we would be anywhere close to finally developing or having a theory of everything? Or I guess at least following, I guess, the main line that people have been proposing anywhere near unifying relativity with quantum mechanics or not?
Yeah, I don't think we're any closer than we've been and we haven't been close, I think, to a theory of everything. Um, I mean, even Hawking gave up on the idea of that there could be a theory of everything.
Yeah.
And so I'm not even convinced that there could be a theory of everything. Um, but we could hope for a theory of quantum gravity.
Mm.
But boy, now that's been a long, long time that people have been trying to work on that. And it doesn't seem like the different research programs have become far more developed than they were like when I started in grad school.
Mhm.
Now the different programs are much more sophisticated than they were. But you can't really say that there's any closer to, um, you know, it being decided which one is the right one, or connecting it with experiment in any way. And so we still seem very far away.
Great. So, and where can people find you and your work on the internet?
Yeah, you just need to go to my name, Craig Callender, then type that in, craigcallender.com. You can come to my website.
Great. So I'm leaving links to that in the description box of the interview. And thank you so much again for taking the time to come on the show. It's been a great pleasure to talk with you.
Oh, it's been great. Wonderful. Wonderful. Thank you very much, Ricardo.
Hi guys, thank you for watching this interview until the end. If you liked it, please share it, leave a like and hit the subscription button. This show is brought to you by Enlights, learning and development done differently. Check their website at enlights.com, and also please consider supporting the show on Patreon or PayPal. I would also like to give a huge thank you to my main patrons and PayPal supporters: Per Ergo Larsen, Jerry Mullerens, Frederick Sundo, Bernardo Seixas, Olaf Alex, Adam Kessel, Matthew Whittingboard, Arno Wolf, Tim Hollis, Eric Alenia, John Connors, Philip Forrest Connolly, Dan Demetrio, Robert Windiger, Rui Inácio, Zup, Mark Neves, Colin Holbrook, Phil Kavanagh, Mikkel Stormir, Samuel André, Francis Fortiago Nunes, Fergal Cossen, Hal Herzog, Nuno Machado, Jonathan Labyrinth, João Linhares, Stantantia, Samuel Correia, Eric Hines, Mark Smith, João Eira, Tom Hummel, Sardus France, David Sloan Wilson, Yacila Dez Araújo, Romain Roach, Diego Londonho Correia, Yannick Punter, Dana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavlo Stasevski, Nelek Bach, Guy Madison, Gary G. Alman, Sam Afzal, Adrian Yeager, Paul Tolentino, João Barbosa, Julian Price, Edward Hall, Edin Bronner, Douglas Fry, Franca Bortolotti, Gabriel Ponce Cortez, Ursula Litsky, Scott, Zachary Fish, Tim Duffy, Sonny Smith, John Wiseman, Daniel Friedman, William Buckner, Paul George Arnaud, Luke Lowacki, Georgios Theophanos, Chris Williamson, Peter Wolozin, David Williams, Diogo Costa, Anton Erickson, Charles Murray, Alex Shaw, Maury Martinez, Coralie Chevalier, Bangalore Atheists, Larry D. Lee Jr., Old Erringbon, Sterry, Michael Bailey, Dan Sperber, Robert Grassi, Zigoren, Jeff McMahon, Jake Zool, Barnabas Radix, Mark Campbell, Thomas Dovner, Luke Nissen, Chris Story, Kimberly Johnson, Benjamin Galbert, Jessica Nowicki, Linda Brandon, Nicholas Carlson, Ismail Benzliman, George Coriatis, Valentin Steinman, Per Crowley, Kate Van Goller, Alexander Hubbard, Liam Dunaway, BR, Masood Ali Mohammadi, Perpendicular, Jonas Hertner, Ursula Goodenough, Gregory Hastings, David Pinsoff, Sean Nelson, Mike Lavigne, and Dios Necht. A special thanks to my producers: Isar Webb, Jim Frank, Lucas Stafiniak, Tom Vanagdam, Bernard Ugni, Curtis Dixon, Benedict Mueller, Thomas Trumbull, Catherine and Patrick Tobin, Giancarlo Montenegro, Alni Ortiz, and Nick Golden, and to my executive producers Matthew Lavender, Sergio Quadriano, Bogdan Kanivets, and Rosie. Thank you for all.